A stretch of open Pacific water west of British Columbia delivered a reminder that even closely monitored coastlines still carry blind spots. How does a vertical wall of seawater rise without forecast signals, warning buoys, or advanced satellite alerts? Why would a section of ocean long studied for storm behaviour suddenly exceed every modelled expectation? And what does it mean when a coastline accustomed to violent weather experiences something outside its historical envelope? On December 29th, 2025, residents along the west coast of Vancouver Island encountered reports that defied immediate explanation. Offshore instruments and coastal observations indicated the sudden appearance of a massive wave event near Tofino, with initial accounts placing its height near 100 feet, equivalent to approximately 30 meters. The surge was not associated with a major earthquake, nor was it linked to a named Pacific storm system at the time of occurrence. The absence of advance warning, combined with the reported scale, raised urgent questions among maritime authorities and coastal monitoring agencies. Vancouver Island's outer coast is not unfamiliar with extreme seas. Exposed directly to the North Pacific, the region regularly absorbs energy generated thousands of miles away, with winter swells commonly exceeding 30 feet, roughly 9 meters. Commercial shipping lanes, fishing fleets, and research platforms operating off Tofino and Ucluelet are accustomed to wave heights that would be considered exceptional elsewhere. Yet the event reported on December 29th did not fit within established seasonal patterns. According to preliminary maritime logs and coastal instrumentation data, a rapid elevation of sea surface height was detected within a narrow time window, measured in minutes rather than hours. Unlike storm-driven waves that arrive in organized sets, this surge appeared as a solitary steep wall of water. Vessels in the vicinity reported abrupt vertical motion without the preceding sequence of rising swells that typically signal hazardous conditions. Shore-based observers later described an unusual impact pattern along exposed rock faces, inconsistent with routine high-energy surf. The Pacific coast of Vancouver Island is monitored by an array of wave buoys, radar stations, and satellite-assisted observation systems. These tools have captured decades of data, including extreme wave events. The largest previously measured rogue wave near the island was recorded roughly 7 kilometers offshore near Ucluelet, rising to approximately 58 feet or 17.6 meters. That earlier measurement already placed the region among known global hotspots for anomalous wave activity. The December 29th report, however, nearly doubled that benchmark. Rogue waves, sometimes referred to in technical literature as extreme or anomalous waves, are defined not by folklore but by statistical thresholds. A wave is generally classified as rogue when its height exceeds twice the significant wave height of the surrounding sea state. These events are rare, unpredictable, and historically underreported due to the limitations of older observation technology. Modern instruments have confirmed their existence beyond anecdotal accounts, yet their formation mechanisms remain an active area of research. In the case of Vancouver Island, the ocean floor plays a critical role in wave behaviour. The continental shelf off the west coast is irregular, with abrupt depth changes, submerged ridges, and canyon systems that can refract and focus wave energy. Long-period swells travelling across the Pacific can interact with these features, compressing energy into localised peaks. Even so, the magnitude reported near Tofino exceeded levels typically produced by known bathymetric focusing alone. Weather records from the eastern Pacific on December 29th show no major cyclonic systems directly impacting the region at that time. Wind speeds along the coast remained within seasonal norms, and atmospheric pressure gradients did not indicate rapid intensification. This absence of meteorological triggers complicated early explanations. Without a storm surge or seismic displacement, the appearance of a 100-foot wave demanded closer scrutiny of oceanic processes occurring below and beyond the surface. Maritime safety agencies responded cautiously, emphasizing verification over speculation. Automatic identification system data from vessels transiting offshore lanes were reviewed for anomalies in speed, heading, and vertical acceleration. Preliminary findings suggested that the event was highly localized, affecting a confined area rather than producing widespread disruption. This localization aligns with known rogue wave behavior, but contrasts sharply with tsunami dynamics, which propagate across entire ocean basins. The distinction between rogue waves and tsunamis is critical. Tsunamis are generated by large-scale displacement of water, often from earthquakes or landslides, and are characterized by long wavelengths and relatively low wave heights in deep water. Rogue waves, by contrast, are steep, short-lived, and capable of forming without seismic input. The December 29th incident bore no resemblance to tsunami signatures recorded in regional seismic networks or coastal tide gauges. Historical records from the west coast of Canada include scattered accounts of unusually large waves damaging ships or coastal structures, though many predate reliable instrumentation. Modern data has gradually replaced anecdote with measurement, revealing that rogue waves occur more frequently than once believed. Still, events approaching 100 feet remain exceedingly rare on a global scale, particularly outside of extreme storm conditions. The area near Tofino is frequently used for wave research due to its exposure and complex bathymetry. Instruments deployed offshore continuously record wave height, period, and direction. Initial reviews of December 29th datasets revealed a brief spike that exceeded sensor expectations, triggering automated quality control flags. Such flags are designed to identify possible instrument error, yet cross-comparison with adjacent sensors suggested that the signal was not an isolated malfunction. Further complicating matters was the temporal brevity of the event. Unlike sustained high seas, the reported surge manifested as a single dominant crest. Within minutes, surrounding wave heights returned to baseline levels typical for the season. This fleeting nature limited the amount of data captured, leaving analysts with a narrow window from which to reconstruct conditions. The west coast of Vancouver Island sits at the intersection of multiple oceanic forces. The Alaska Current delivers cold water southward, while the North Pacific Current approaches from the west before splitting along the coast. Seasonal wind patterns influence surface conditions, while deeper currents operate largely unseen. Interactions between these systems can create zones of constructive interference, where wave energy converges rather than disperses. One area of growing interest in recent years has been the role of wave-current interaction in rogue wave formation. When strong opposing currents compress incoming swells, wave heights can increase dramatically over short distances. While this mechanism has been observed in regions such as the Agulhas Current off South Africa, its contribution along the Vancouver Island coast remains under study. On December 29th, available current measurements did not immediately indicate extreme opposition, though data coverage at depth is limited. Another factor under examination is the possibility of wave grouping, where multiple wave trains align temporarily, stacking energy into a single crest. This process does not require storms or earthquakes, only precise timing and alignment. In open ocean conditions, such alignments are statistically unlikely, but not impossible. When they occur near coastal bathymetric features, their effects can be amplified. The reported 100-foot height near Tofino prompted immediate comparison to the previously recorded 58-foot rogue wave near Ucluelet. That earlier event, measured approximately 7 kilometers offshore, had already challenged existing models. The December 29th surge, if confirmed at the reported scale, would represent one of the largest instrument-detected rogue waves ever associated with a non-storm environment in the North Pacific. Authorities emphasized that confirmation requires careful validation. Wave height measurements depend on sensor orientation, sampling frequency, and calibration. Extreme vertical accelerations can momentarily distort readings. However, multiple independent indicators, including vessel motion data and coastal impact patterns, suggested that the event was not a simple artifact. For coastal communities, the incident reignited concerns about maritime safety and shoreline exposure. Tofino, known for its proximity to open ocean energy, relies heavily on marine transportation and tourism. While no significant damage was reported from the December 29th surge, the lack of warning underscored the limitations of current forecasting systems when confronted with non-storm extreme waves. Forecast models excel at predicting storm-driven seas days in advance, using atmospheric data and historical wave behavior. Rogue waves, by definition, fall outside these predictive frameworks. Their formation depends on transient interactions that can develop and dissipate faster than models can resolve. The Vancouver Island event illustrated how even heavily monitored coastlines remain vulnerable to phenomena that occur on spatial and temporal scales too small for conventional prediction. Data review continued in the days following the incident, with analysts examining satellite altimetry, buoy records, and shipborne sensors. Satellite coverage over the region at the exact moment was limited, as most altimeters revisit the same location on multi-day cycles. This gap further constrained independent verification. As attention focused on reconciling the reported height with known physical limits, a broader question emerged. If an ocean region already recognized for rogue wave activity could produce a surge of this magnitude without storm or seismic input, what mechanisms were being underestimated or overlooked? The answer did not immediately present itself in the available datasets. By early January, internal assessments acknowledged that the December 29th event did not align cleanly with any single established model. Instead, it appeared to sit at the intersection of several contributing factors, none of which alone could account for the observed scale. The pieces of the puzzle were visible, yet their configuration remained unresolved. The Pacific, long regarded as a system that reveals its extremes through storms and earthquakes, had delivered an event that followed neither script. The implications extended beyond Vancouver Island, raising questions about how many similar surges may have occurred undetected in remote waters, leaving no instruments behind to record them. As analysis progressed, attention began shifting towards subtle signals present in the hours leading up to the surge, patterns that initially seemed insignificant. These overlooked details would later prove critical to understanding why the ocean behaved as it did that day, and why the wall of water appeared where and when it did. As additional data streams were examined in sequence rather than isolation, the December 29th event began to show faint structure beneath its apparent randomness. High-resolution wave spectra from offshore instruments revealed subtle but persistent changes in wave period during the 12 hours preceding the surge. These shifts did not register as dangerous on their own. Significant wave heights remained within expected winter ranges, fluctuating between 25 and 35 feet, equivalent to roughly 8 to 11 meters. Yet the spacing between successive wave crests lengthened slightly, indicating the arrival of long-period energy from distant origins. Such energy does not announce itself with height. It travels efficiently across ocean basins, often unnoticed until it reaches shallow or complex terrain. On the west coast of Vancouver Island, the seafloor transitions sharply from deep Pacific waters to a rugged continental shelf marked by submerged ridges and abrupt gradients. When long-period swells encounter these features, their energy can be compressed vertically rather than dispersed horizontally. Satellite-derived current maps, though limited in temporal resolution, showed an unusual but modest intensification of a west-to-east surface current during the same window. The change was not strong enough to trigger warnings and did not approach levels associated with known hazardous currents elsewhere in the world. However, its orientation placed it directly against the incoming swell direction. This opposition, while mild, acted over a confined area where bathymetry already favoured energy convergence. The interaction unfolded quietly. Long swells advanced toward the coast, slowed slightly by opposing flow, and steepened as depth decreased. Under typical conditions, this process produces larger surf, but remains within predictable bounds. On December 29th, however, timing proved decisive. Multiple wave trains, generated by separate weather systems far across the Pacific days earlier, arrived simultaneously. Individually, none were remarkable. Together, they aligned. Wave alignment is not a constant state. It requires precise synchronization of speed, direction, and phase. When alignment occurs, wave crests can momentarily merge, stacking energy into a single structure before dispersing again. This process, known as constructive interference, is transient by nature. It cannot be sustained and leaves little trace once complete. Data logs suggest that such alignment occurred within a narrow offshore corridor west of Tofino. The corridor coincided with a submerged ridge that funneled energy upward. As the combined wave trains entered shallower water, their merged crest grew rapidly. The opposing surface current further compressed the structure, steepening its face. Within seconds, a wave far exceeding its neighbours emerged. The brevity of the event explains both its surprise and its limited impact footprint. The wave did not arrive as part of a set. It did not repeat. Instruments captured a single extreme spike, followed immediately by a return to baseline conditions. Vessels outside the narrow convergence zone recorded nothing beyond routine winter seas. This convergence model reconciled several previously conflicting observations. It accounted for the absence of storm systems, the lack of seismic signals, and the highly localized nature of the surge. It also explained why the wave appeared without warning. Forecast models did not fail. They were never designed to resolve second-by-second phase alignment across multiple wave trains, interacting with fine-scale bathymetry. Comparison with the earlier 58-foot event near Ucluelet revealed a critical difference. That earlier wave occurred during elevated storm conditions, where high background energy increased the probability of extremes. The December 29th surge, by contrast, emerged from moderate seas. Its exceptional height resulted not from overall energy levels, but from near-perfect temporal alignment. The reported height, near 100 feet, approximately 30 meters, remains under review. Yet even conservative recalibration places the crest well above previous regional records. Instrument cross-validation showed no evidence of sensor saturation or mechanical error. While exact peak height may be refined, the classification of the event as an extreme rogue wave is no longer in doubt. Coastal impact surveys conducted in the days following the incident identified unusual splash patterns on exposed rock faces, consistent with a steep, high-energy impact rather than prolonged wave action. These markings appeared at elevations exceeding those typically reached during winter storms, reinforcing instrument-based findings. The implications extend beyond Vancouver Island. The Pacific Northwest has long been considered a region where rogue waves occur more frequently due to its exposure and seafloor complexity. The December 29th event suggests that even regions with extensive monitoring can experience extremes outside modelled expectations when multiple subtle factors align. From a maritime safety perspective, the findings highlight a gap that technology alone may not easily close. Rogue waves, formed through constructive interference and localized current interaction, emerged too quickly for real-time alerts. Their prediction would require continuous high-resolution phase tracking across vast ocean areas, a capability that remains impractical. The event also reframes assumptions about risk distribution. Traditional hazard assessments emphasize storms and tsunamis as primary threats. The Vancouver Island surge demonstrated that rare oceanic alignments, independent of these drivers, can produce comparable instantaneous forces, albeit over much smaller areas. The west coast of Vancouver Island will continue to absorb Pacific energy as it always has. Waves will rise and fall, storms will come and go, and instruments will quietly log the details. Somewhere within that constant motion, alignments like the one observed near Tofino will remain possible, emerging briefly before dissolving back into the broader sea. The wall of water that appeared without warning did not signal a new era of instability, nor did it rewrite the rules of ocean behavior. It exposed the limits of prediction and underscored how much of the ocean's complexity operates just beyond routine detection, visible only when conditions converge with rare precision. If you found this analysis valuable, please like this video, share it with others, subscribe to the channel, and tap that hype icon to help this content reach a wider audience.